Hello, my name is Ebasraman Iwa, and I'm going to be presenting the carbon cycle and the nitrogen cycle for chapter 28. Carbon is the essence of life and is everywhere. To grasp the global climate change, we must know its sources, sinks, and forms. Sources like microbes and fossils, fuel burning, release carbon as CO2. Sinks such as plants and phytoplankton absorb CO2. Carbon exists in various forms: reduced, like methane, and oxidized, like CO2. The cycle begins with carbon's fixation, converting CO2 into organic matter. While plants are crucial, microbes, especially in the oceans and deep sediments, also fix carbon. Marine microbes like Prococcus and Cyanococcus play a big role. Even in dark, deep sediments, bacteria and archaea contribute significantly. In addition to carbon dioxide, methane can be formed without oxygen by certain microorganisms, mainly archaea. They use hydrogen plus either CO2 or acetate to create methane. Methane created in sediments can be consumed either with oxygen by bacteria or without oxygen by archaea and dinitrifying bacteria. Large amounts of methane are also produced in the digestive systems of ruminant animals. Other significant methane sources globally include sediments in rice paddies, coal mines, and sewage plants. Okay. Microorganisms, both using sunlight and chemicals, fix carbon from the air. Methane comes from underground gases or decaying matter. Special bacteria convert harmful carbon monoxide from vehicles and industry back into safe CO2. And the red arrows show processes with oxygen, stripes show mixed conditions, and purple arrows lead to methane production without oxygen. All carbon from fixed sources eventually become organic matter, which can be broken down into CO2 through various processes like aerobic and anaerobic respiration and fermentation. However, the depiction oversimplifies things because organic matter varies widely in its composition, structure, and how easily it can be broken down. The breakdown of organic matter depends on factors like the environment, oxygen levels, availability of other nutrients, and abiotic conditions like pH, temperature, and osmotic conditions. The types of microorganisms present also plays a role. Complex or organic substances like lignin found in mature plants are particularly tough to break down. They are made up of complex polymers with strong bonds. Certain fungi and bacteria produce enzymes to break down lignin, but it's a slow process that often requires oxygen. Under anaerobic conditions, some microbes can break down lignin, but it's much slower, and this can lead to the accumulation of undergraded organic material like peat bogs. The nitrogen cycle. Nitrogen fixation kicks off the nitrogen cycle, where certain bacteria and archaea turn atmospheric nitrogen into ammonia. This ammonia is then used to make essential organic compounds. These nitrogen fixing microbes work in various conditions, some even with oxygen around. Bacteria is like Bacteria like azotobacteria and cyanobacteria like Tridom like this bacteria do it in the air, while others like Clostridium manage without oxygen. In nature, certain bacteria buddy up with plants like legumes to help them fix nitrogen. For example, rhizobia bacteria team up with legumes to do this job. Other bacteria assist different plants like Frankia with shrubs and cyanobacteria with water ferns like Azolla. These help bacteria These helpful bacteria are vital for farming as they help plants grow by providing them with essential nitrogen. When nitrogen is fixed from the air, it becomes ammonia, which is immediately used to build up important organic molecules like proteins and nucleic acids. Later, when these organic molecules break down, nitrogen is released back into the environment as ammonia. Ammonia can only donate electrons, so during nitrification, it's converted first into nitrite, and then into nitrate, with oxygen as the final electron acceptor. For a long time, it was believed that the different bacteria did not each step. Okay. For a long time, it was believed that different bacteria did each step of nitrification, but now we know some bacteria, like Nitrospira species, can do both steps. This ability is called complete ammonia oxidation. Nitrifying bacteria do this process to get energy and electrons. Lastly, nitrate, a form of nitrogen, is crucial because it can be used by microbes and plants to make their own cells in a process called assimilatory nitrate reduction. Alternatively, some microbes use nitrate when there's no oxygen around, but the nitrogen isn't used for making cells. This is called dissimilatory nitrate reduction. When nitrate is completely reduced into nitrogen gas, it leaves the ecosystem and returns to the atmosphere in a process called denitrification. This is done by certain bacteria like Pseudomonas species and can produce greenhouse gases like nitrous oxide. Another important process is called ammox and also removes ammonia from the environment by directly turning ammonium and nitrate into nitrogen gas without forming nitrate first. This discovery is significant for wastewater treatment where high ammonia levels are a concern. And I'm done.